Hello dear friends, welcome to a lecture on numerical analysis. In this lecture, we shall study numerical solution for ordinary differential equations, and we shall study two methods. One is Taylor's series, solution by Taylor's series method. Here we shall obtain differential equation solution as y, and y will be a series in powers of x. The next method we will have is Picard's method. There we will have a tabulated values of x and y, which is a method of successive approximation. We consider ordinary differential equation, simplest differential equation we shall consider, and that is the first order differential equation. Here we have written, consider the differential equation y dash, or this dy by dx or y prime is equal to f of x comma y, function of x and y, and with the initial condition y at x naught is equal to y naught. There are two types of problems usually we consider as initial value problem and boundary value problem. In initial value problem, the condition is specified at the initial point. Here the initial point is x naught. The value of y at this initial point x naught is given in the problem itself, and that value is given as with notation y naught. So, thus this type of problem is known as initial value problem. The condition is given at initial point. And for boundary value problem, for equations of second and higher order, the values are specified at some points, more than one point, and that problem is known as boundary value problem. Here we will consider initial value problems, and the equation we have written here is y dash is equal to f of x comma y, and the initial condition is y at x naught is equal to y naught, and we assume that y of x is the exact solution of this differential equation, and we expand this function y of x using Taylor series about a point x is equal to x naught, and we know the Taylor series is given with this expression: y of x is equal to y naught and plus x minus x naught, y naught dash derivative of y at x is equal to x naught, plus, that is the notation, plus x minus x naught whole square divided by 2 factorial y naught second derivative at y of y naught, and plus x minus x naught cube divided by 3 factorial third derivative of y at x is equal to x naught. So, this is the expression for Taylor series, and we know usual form of Taylor series is f of a plus h, that is this form f of a plus h is equal to f of a plus h f dash at a plus h square by 2 factorial second derivative of f at a plus etc. And this form is may be written in different way, and here we have considered that form as like this, where the function is taken as y of x. We may consider this this can be converted to Maclaurin's series, and a plus h can be taken as x, and we denote that function as y, and y of x is written in terms of y naught. The derivative is at this y at x is equal to x naught, and power series for about the point x naught, about x is equal to x naught, the series is developed and it has this form. If we get the values of y naught dash, y naught double dash, or third derivative of y at x is equal to x naught etc. are obtained, then this gives the solution of the differential equation 1. So, therefore, we have to remember the Taylor's series for the function y of x at point x is equal to x naught. Now, we shall solve this problem. I have written problem here from the Taylor series for y of x. Find y at 0.1 correct to 4 decimal places, where the differential equation is y dash or y prime, or that means dy by dx, and is equal to x minus y square, and y at 0 is equal to 1. So this is the, if you compare this, the differential equation, function f of x comma y is x minus y square, and the initial condition is y at x naught is equal to y naught, means here x naught is equal to 0 and y naught is equal to 1. These are the values of x naught and y naught, here it is, and this is the value of f of x comma y function. And we should write this series, Taylor series, and then find the values of y naught and its derivatives to get the solution. So we start the solution as here. We shall first write the function f of x y. We have f of x comma y, that is x minus y square. This is our function, and that is actually y dash, and given y at 0 is 1, that is y at x naught is equal to y naught. Therefore, x naught is 0, y naught is 1. Now the Taylor series we shall write here from 2. We have Taylor series as y of x is equal to, now we note the value of x naught is 0, so therefore we can directly write the series on the right side by putting x naught is equal to 0, and this gives the form y naught plus x naught is 0, so it is only x y naught dash plus x square by 2 factorial, second derivative of y at x is equal to x naught. This is the meaning of y naught, second derivative of y naught, and plus x minus x naught, that is x cube, divided by 3 factorial, third derivative of y at x naught, plus, now the series is infinite, and we are asked to get the values correct up to 4 decimal places. So we should write few more terms, and the next term will be x power 4 divided by 4 factorial, fourth derivative, and that notation we shall write like this: y naught, this is the fourth derivative of y at x is equal to x naught, plus x to the power 5 divided by 5 factorial, fifth derivative of y at x is equal to x naught, and plus so on. So this is the Taylor series. Originally we have written this, and it takes this form because x naught is equal to 0. If x naught is non-zero, then we should write in this form, x minus x naught, etc. And now the next our next step will be, we have to calculate these values, y naught, the derivative of y naught, first derivative, second derivative, third derivative, etc. Now we obtain these values and substitute these values in this equation. So further we will have to compute these values, and for that purpose we see the original function. Now we have what is y dash that is given. Y dash is x minus y square, and therefore this value, actually the first value is given as y naught is equal to 1. So we have y naught is equal to 1, and y dash is given as x minus y square, and therefore this will be y dash at x is equal to x naught, means x naught is here, we have x naught is 0, and therefore this value is 0 minus y is now y naught. At initial point we have to use the values, and that is 1. So it is 0 minus 1 square, which is minus 1. And next is now this is y double dash here from this, and from this we have to obtain the derivative using the rules and formula from differentiation. So derivative of x is 1 minus derivative of y square with respect to x, that is 2y into y dash, derivative of y with respect to x. So this is the derivative of y square, you note it, 2y into y dash, because 2y into dy by dx, a term in y is first differentiated with respect to y and then multiplied by derivative of y, and therefore the second order derivative of y at x is equal to x naught. Now we should use the earlier values. It is 1 minus 2. What is y? Y is 1. At y naught we are using this value. So it is 1 and y dash means this is minus 1. So thus this becomes 1 plus 2, that is 3. Next third order derivative is from this. It is 0. 0 minus 2, and we have to use the product rule here to differentiate this y into y dash. So first function is y, derivative of the second will be second order derivative of y, plus, and because there is minus sign it will be again minus 2, and derivative of this first function is y dash into y dash, and that will be y dash square. So thus this is the third order derivative at x is equal to x naught, means x is 0, and that is equal to minus 2. What is y? Y is this value 1, and y double dash, this value is 3, minus 2 y dash is minus 1 and its square. So this value is minus 6, and this is minus 2, that is minus 8. This becomes plus 1. So minus 6 minus 2 is minus 8. This is the third order derivative. Now next is fourth. We shall obtain the fifth order derivative up to 5 terms we have written, because we have to obtain the solution correct up to 4 decimal places. So fourth derivative of y from this, it is again minus 2. We have to use the product rule. Y into derivative of y double dash is y triple dash, third order derivative, and again minus 2, derivative of y is y dash y double dash. So this much is the derivative of the first term, minus. Now what is the derivative of the second term? Minus 2 into y dash square, derivative of y dash square is 2y dash into y double dash. So minus 2 into 2, that is minus 4 y dash into y double dash, and you see this is minus 2y triple dash minus these are the same terms. So minus 2 minus 4 means minus 6 times y dash into y double dash, and thus this value of fourth derivative at 0 is, and I shall write here, therefore y naught, fourth derivative at x is equal to x naught, and this is minus 2 into y is 1, y triple dash is minus 8, and next is minus 6, y dash is minus 1, and y double dash is 3. So minus 1 into 3, see the product of these two, I shall write directly, that is minus 3, and if you see the calculation, it is minus 2 into minus 8, that is 16 plus 18. So 16 plus 18, that is 34. And now the fifth order derivative of this, that is minus 2, use the product rule. So y, fourth order derivative of y, and again minus 2 y dash, derivative of the first, second as it is. So this much is the derivative of the first term. Next is minus 6 y dash into the derivative of y double dash, which will be y triple dash, and further minus 6 into derivative of y dash, that is y double dash into y double dash, that is y double dash square. So this much is the derivative, and you see this value at 0, so that is I shall write here. Therefore, y fifth order derivative at x is equal to x naught, and this is minus 2 y is 1. Fourth order derivative here we have obtained is 34, and this is minus 2 into minus 6, that is minus 8. So, minus 8 times y dash, what is y dash is minus 1 and y triple dash is minus 8. So, minus 8 into this is, you see these two values product, y dash and y triple dash, that is y dash is minus 1 into minus 8, that is 8, and this is minus 6, and you see square of y double dash is 3 square is 9. So, this value comes to be, this is minus 68, and this is minus 64, and this is again minus 54. So, this is 186 negative, minus 186. So, these are the values we have obtained for the derivatives. Now, we substitute these values in this Taylor series to get the solution, and therefore, substituting these in 1 we get this in the Taylor series, or we may suppose this as 1. Substituting these in 1 we get y of x is equal to see y of x is y naught. What is y naught is 1 plus x into y naught dash is minus 1. So, it is minus x, 1 minus x, and then further x square by 2 factorial y double dash at this x is equal to x naught is 3. So, it is 3 by 2 factorial, that is plus 3 by 2 into x square, and plus now x cube by 3 factorial y naught triple dash is minus 8. So, this is negative minus 8 upon 3 factorial, 3 factorial is 6, and into x cube. Next is plus x raised to 4 by 4 factorial, and fourth order derivative here we have is 34. So, 34 divided by 4 factorial, see 4 factorial is 24 into y naught fourth derivative, see into x power 4, we have written this value x power 4, and next plus, so this is this derivative is negative, so therefore this sign will be negative, minus 186 divided by 5 factorial is 120 into x power 5, and plus so on. So, this is the series for y of x, and this can be simplified. See this is which is equal to 1 minus x plus 3 by 2 x square minus, this can be reduced or can be written in brief form, and which will be 4 by 3 dividing by 2 x cube, and plus this is 17 by 20, this will be 12, 17 by 12 dividing by 2 x power 4 minus, and this can also be divided by 6. So, this is 31, this is 31 dividing by 6, and this is 20 x power 5, and so on. So, we are asked to find the value of y at x is equal to 0.1, and therefore putting x is equal to here 0.1, we get y at 0.1 is equal to 1 minus 0.1 plus 3 by 2 0.1 square and plus 4 by 3 0.1 cube and so on, plus 17 by 12 0.1 power 4 and minus 31 by 20 and 0.1 to the power 5 and plus so on. So we can use calculator and to obtain this value, and using calculator the value becomes, so I have calculated this, and that value is, this value comes to be 0.9138. You should check this using a calculator. So thus we can use Taylor series method to obtain a series solution for a differential equation. Now we shall see what is the next method is Picard's method of approximation. See how we have obtained the values here. We are using the differentiation rules and formulae. We have written the derivatives, and that values are obtained at initial point, where the initial point is given in the problem itself, initial condition. Now the next method we shall see is Picard's method. Method of successive approximation. We consider the same equation, differential equation, as in the Taylor series method. Consider the differential equation. Y dash is equal to f of xy with the initial condition, the same initial condition with the initial condition which we have written earlier as y at x naught is equal to y naught, and we suppose this together as equation 1. First what we shall do is integrate this. Integrating this equation we get, so integrating and from the in the interval x naught to x, integrating we get, see integration of y dash is y, antiderivative, integration is antiderivative, and therefore here we get y. And on the right side we can integrate from x naught to x, the function is f of x comma y into dx plus a constant of integration c, and this constant is determined using the initial condition. So that is the use of the conditions given, initial and boundary conditions we are used to obtain the value of constants, arbitrary constants obtained in the process of integration. And using this condition, that means when x is x naught, y is y naught. So using the condition y of x naught is equal to y naught, that is x is equal to x naught, y is equal to y naught. So what we shall get, this is y naught, left side, y is y naught and x is x naught. So integration is x naught to x naught, x is x naught, and this is f of x comma y, the function, and into dx plus a constant. But you see here this integral x naught to x naught, this integral, or here also we can write the function is f of x y, and then the value of x is to be used as x naught and y is to be used as y naught. But this integral, the initial limit, lower limit and the upper limit are the same, and therefore the value of this integral is 0, and thus we get y naught is equal to 0 plus c, or that is c is equal to y naught, and put this value of c here in the equation, and thus the equation becomes, therefore we have y is equal to, y is, we can write this c first, and which is y naught plus integration x naught to x f of x comma y dx. So this is our integral equation, and we suppose this as second. This is an integral equation because it involves integral. And see, we can integrate this by taking the values of y, different values of y, and in succession we get the different approximations. And for the first approximation of y, we consider y is equal to y naught. So we take first approximation for y as y naught and put this in the right side of 3 in the integrand, and we denote it by this approximation, first approximation for y as y naught, and we denote denote it by y1, first approximation. This is y1 means first approximation, and thus what is y1? Y1 we will have as, what we are doing is we are taking this first approximation for y in the integrand. See, y as y naught in the integrand. In the integrand we have to take, and we denote this approximation of y as y1. This y will be y1. So we get y1 first approximation is equal to y naught plus integral x naught to x f of x comma y naught into dx. So this is our first approximation, and now we get the value of y1 from this. After integration, obtain y1 from this. And put it in the integrand in the second, integrand on RHS of second, and substitute it in the integrand on RHS of second to get second approximation. Next, second approximation as y2, and thus what will be y2? Y2 will be, now see, what we have to do is put the value of y as y1, and that will be y naught. No change in this first term, y naught, no change in the limits of integration, you know this. Only we are changing the value of y in the integrand, this value, no change in x, and thus this will be f of x comma, now it is y1, first approximation. First we have put the first approximation as y naught, that is initial approximation as y naught, and then we obtain y1 and use that value of y1 here to get the second approximation. Proceeding like this, we obtained, proceeding like this, we obtain y3 etc. y3, y4 and so on. Third approximation, fourth approximation, n minus 1th approximation and nth approximation, where what will be nth approximation? By observation we can decide. So this is first approximation, this is second approximation, and thus the nth approximation will be y naught is fixed, y naught plus integral x naught to x, that is also fixed, f is fixed function, and x, no change in x, only this y changes. See here, second approximation, here y is first approximation, here nth approximation and this value of y will be n minus 1th approximation, and where this y naught is initial approximation, y naught is y at x naught, so that is initial condition. And thus this is the formula for Picard's successive approximation. N takes value 0, 1, 2, etc. So this formula we have to remember, and using this formula we get a sequence. So we get a sequence, which is the sequence here, that is y naught, or this value can be denoted by 0th approximation or initial approximation, y1, y2 and so on, yn. This converges to the solution of the differential equation 1, which converges to the solution of solution y of x of 1. And there is a condition that this function f of xy must be bounded, and that must satisfy Lipschitz condition. Then this sequence converges, and which gives the solution. This is the Picard's successive approximation method. Now we shall solve a problem on it. So I shall write a problem here. See, problem on Picard's method is given the differential equation, see, for the differential equation dy by dx is equal to x square divided by y square plus 1. This is y square plus 1 with the initial condition y0 is equal to 0. Use Picard's method. To obtain y for these values of x, y for x is equal to 0.5, 0.5 and 1. Correct to 3 decimal places. So this is the problem. Now we shall solve it. We have written the method here, and the formula for Picard's successive approximation also we have written, and this is the formula. So we should have the function, this is f of x, y. Now write as a solution. See, we have what is f of x comma y, that is the function x square divided by y square plus 1, and condition is y at x naught, y at 0 is equal to 0, means that is x naught is equal to 0, y naught is equal to 0. This is x naught and this is y naught. Y at x naught is equal to y naught is the condition. So therefore the value of y naught is on the right side, that is 0, and this is the value of x naught, which is also 0. So thus the Picard's method we have is y naught, and this is the formula for Picard's approximation will be. And you see, we have by Picard's method y is equal to y naught plus integral x naught to x f of x comma y into dx. This is initial equation or first step in the Picard's method, first equation in Picard's method, and from that what we can write is y is equal to y naught is 0, you see, and that is given. Not every time, but here in this problem that value is given as 0, and thus this is integral. So this is 0. So integral x naught is again 0 given. So it is 0 to x, f of x comma y, that is x square divided by y square plus 1. And you see what is the value of for the first approximation. For the first approximation we should have to write n as 1, and here y naught is 0, and what is the value of y square. So this is 0 square, y naught square plus 1 into dx, and this will be integral 0 to x, x square divided by 0 square, y naught is 0, so 0 square plus 1, that is 1 dx, or it is just integration of x square, that is x cube by 3. Limits are 0 to x, so it will be only x cube by 3. You can check it. This is our first approximation, y1. Now what about the second approximation? For the second approximation we should use this formula, this one, and thus further. Next, what is y2? y2 is equal to integral 0 to x square. So from this f of xy is x square divided by y square plus 1, that is x square divided by, that is now y1 square. Here it is y naught square, now it will be y1 here as square plus 1 into dx, and that is integral 0 to x square. What is y1 square? y1 is x cube by 3, so it will be x cube by 3 square plus 1 into dx. Now we have to evaluate this integral, and that can be evaluated by the method of substitution. You see, this is x cube by 3, and here we have x square term, so we can use substitution for this bracket. So put x cube by 3 is equal to t, and thus the integration of this derivative of this will be 3x square by 3, that is only x square. So x square dx will be dt, and we may observe when the x is 0, t is 0, and when x is x, t is x cube by 3, and therefore this integration becomes. So therefore what is y2? Second approximation will be integral 0 to t. This is the method of substitution we are using to evaluate this definite integral 0 to t, and not t but x cube by 3. The value of t is x cube by 3, and this is x square dx. X square dx is dt divided by, and you see what is the denominator, that is t square plus 1. So integration of this is tan inverse t. dt divided by t square plus 1 is tan inverse t, and that is tan inverse t. The limits are x cube by 3 and 0, and thus this is we expand this using Taylor series again for tan inverse x, and that will be x cube by 3 minus, what is the Taylor series for using this tan inverse x? It is x minus x cube by 3 plus x power 5 by 5 and minus so on. So therefore this will be in here we have actually this is tan inverse, or I shall write here tan inverse of x cube by 3 minus tan inverse of 0, but tan inverse of 0 is 0, and therefore only this is tan inverse of x cube, tan inverse of x cube by 3, and the series expansion for this is, now in place of x, here is x cube by 3. So this is the series expansion, and that will be x cube by 3 minus x cube by 3, it's cube. So x cube by 3 cube divided by 3, and that will be x cube by 3 divided by 3 divided by 3, and plus x cube by 3 raised to 5 divided by 5 and minus so on. So this is what we have obtained is y2, and we may see this y1 has first term x cube by 3, y2 also has first term x cube by 3, and next terms are the higher power terms, that is x raised to 9 divided by 3 cube into, that is 3 power 4, which is 81, and so on. So that's the expression for y2 is y2. We have used this formula or series, Taylor series for tan inverse x here, and thus y2 will be x cube by 3 minus, this is x power 9 divided by 81, and next is plus, what will be this, that is x power 15 divided by 3 power 5 into 5 into 3 power 5 and minus so on. So this is the second approximation, and the first approximation has this term x cube by 3, second approximation also has the term, same term, and therefore for to get the decimal places, 3 up to 3 decimal places, we are asked to obtain the expansion for this function y at 0.25. So to find y at x is equal to 0.25, 0.5 and 1. So we are asked. So for 0.25, first we shall see these values up to 3 decimal places. Now up to 3 decimal places means we should have this term to be more than 3 decimal places, that is first 3 decimal places to be 0 for this term, so that this value will remain the same. Now to get solution correct up to 3 decimal places, we should take the value of x. The value of x such that this term x power 9 divided by 81 must be less than or equal to 0. These 3 decimal places should be here 0, so that the solution will be correct, or this will give the correct up to 3 decimal places, because we can neglect the further terms. If this value is less than or equal to 0.0005, say, suppose the fourth decimal may be 5 or any other non-zero maybe, and thus if these 3 decimal places are 0 after this decimal, these 3 digits are 0, then we get the further powers also will be these 3, at least 3 places will have 0, and thus the solution will be correct up to 3 decimal places. And this gives this gives x power 9 is less than or equal to some value, and that can be calculated from the calculator, and this here we have x must be less than or equal to 0.7. You can verify this, we multiply this and take the 9th root on both sides, and that gives x is less than or equal to 0.7, and this is the condition to get the solution from the first term. This is the first term, this is the first term, because we have assumed this term is less than or equal to this value, and for this we are asked to find the values at these places. So these 0.25, 0.5 are less than 0.7, and therefore this first term only gives the solution at these 2 points, and for 1 we have to consider this one more term, because the value of 1 is greater than 0.7. So therefore we have now we have for y at 0.25 is equal to, from the first terms in the series here for this approximation, y at 0.25 will be 0.25 cube divided by 3, and this value will come to certain number, and that number I have calculated here. So that is see, this is 0. You can use calculator to obtain this value. And similarly, next is y at 0.5, that is from this first term only. We don't need to take the second term because the solution is asked correct up to 3 decimal places. If you substitute the value in the next, at least earlier these places will be 0 and we have to take only 3 decimals. So this value is 1/3 0.5 cube, and that comes to be 0.042. And but for y at 1.0, we need to take this value also, these two. And because this is for the two, only first value gives the solution for x less than 0.7. 1 is greater than 0.7, and therefore we need to take two terms. Correct to 3 decimal places, x cube by 3, that is 1 cube by 3, or which is 1 cube by 3 minus 1 raised to 9 by 81, or which is 1/3 minus 81, and this value is 0.321. You can check using the calculator. Thus we have used the Picard's method of successive approximation to find the values of y at given certain points of x. So these are the values of x. We are asked to find the value of y. In this way, we can use the Picard's method of successive approximation to solve a differential equation. So please observe these steps and try to understand it. Thank you for watching the lecture.